We're going to spend this next unit looking specifically at the gas state of matter. There's some general properties of gases that we can observe. First of all, they can be compressed into a smaller volume because the molecules are so spaced apart. Secondly, gases expand without limit so that those gas samples will completely occupy the volume of whatever container it's in. Thirdly, gases exert pressure on their surroundings. And fourthly, gases diffuse into each other, which means they mix, so that two samples placed in the same container will mix completely. We're going to look at four basic properties. We'll look at the amount of gas, which is moles. We'll look at gas volume, temperature, and pressure, and we will relate those in equations of state. Pressure of a gas. Molecules of a gas are in constant motion. They are continuously hitting each other and the walls of their container. And these collisions create pressure. Pressure is defined as the force of those gas molecules divided by the area. The most familiar gas to us is air. Air is comprised mostly of nitrogen, about 78% nitrogen, 21% oxygen, about 1% argon, and then a very small amount of carbon dioxide, if we exclude water vapor from that. In 1643, Torricelli constructed a device to measure the pressure of the atmosphere, or the atmospheric pressure, and he called this a mercury barometer. A barometer is simply a long glass tube which is sealed on one end and it's filled with mercury. The tube's inverted and it's supported in that container of mercury that's open to the atmosphere. So here is what a simple barometer looks like. Atmospheric pressure pushes down, and as atmospheric pressure pushes down, it forces the mercury up the tube, and the tube is marked just like a thermometer in increments, and we will measure this in millimeters of mercury. So the mercury will be supported by the atmospheric pressure. 760 millimeters of mercury is equal to 1 atmosphere. Barometer is going to measure in millimeters of mercury, but the common unit for us is an atmosphere. So a barometer measures atmospheric pressure, and atmospheric pressure is the pressure pushing downward. A mercury manometer consists of a glass tube that's partially filled with mercury. Now a manometer measures gas pressure. One end of the manometer is open to the atmosphere, the other is connected to a container of gas, whatever gas we want to measure the pressure of. The pressure of the gas in the container is equal to the atmospheric pressure plus or minus the difference in mercury levels. So here's what a manometer looks like. It's a U-shaped glass tube, and what we're interested in is the difference in height of the column of mercury. Here's our mercury right here. H is the difference between the heights of the mercury column. So there's my value for H. Here's the gas that I'm trying to measure, the pressure of that gas. And the pressure of the gas will be equal to the pressure of the atmosphere plus or minus whatever this value for H is. And so a manometer will measure gas pressure. Here are some common units for pressure. Now, the most common to us, we're going to use the atmosphere quite a bit. We will use millimeters of mercury, and we will use pascals. Those are the three most common for us. But here are your conversions from atmospheres to millimeters of mercury, 760, to PSI. PSI we don't use at all because that's an American unit. Pascals is the SI unit, 101,325 pascals. And then bar is another common unit, but we don't use that too much in this class. Gas laws, we're going to look at some relationships. The first one is the pressure-volume relationship. It's called Boyle's law. This law came about in 1662 when Robert Boyle did some experiments relating volume to pressure, and he had constant temperature on these gases. And what you'll notice in this particular chart is pressure goes up. These are 4 different trials, but in each trial the pressure went up, and notice what happened to the volume. The volume went down. Exactly opposite. So as pressure goes up, volume goes down, and vice versa. It's an inverse relationship. But what's important in an inverse relationship is this column over here, pressure times volume. those numbers are fairly consistent across the board. So when I take the pressure times the volume, I get a fairly consistent value. When you graph an inverse relationship, here's what the line looks like. Here are those 4 points that were on that last chart. And when you graph an inverse relationship, here's what it looks like. So Boyle's law says the volume of a fixed amount of gas maintains at constant temperature is inversely proportional to pressure. So as volume goes up, pressure goes down. So Boyle's law says this: volume is proportional to 1 over P. We don't like that proportionality sign. We like to get an equal sign. In order to get an equal sign, we have to introduce a proportionality constant we'll just call K1. It doesn't matter what the value for K1 is, because K1 equals P1 times V1. It also equals P2 times V2. We're used to seeing Boyle's law like this: P1 times V1 equals P2 times V2. So that's an inverse relationship. I multiply the initial pressure times the initial volume, set that equal to the final pressure times the final volume. And this is what we're going to use for Boyle's law. So when you have a Boyle's law problem, it will say something about what happens to the volume if the pressure is changed. Let's look at this example right here. A sample of gas occupies 10 liters at a pressure of 1 atmosphere. What will its volume be if the pressure is increased to 2 atmospheres? Now it's important that the temperature stays constant in Boyle's law because temperature is not in the equation. Setup looks like this. Initial pressure, we can leave it in atmospheres. Initial volume, we can leave it in liters. The units really don't matter as long as they're the same on both sides of the equation. P2 is 2 atmospheres. And we're looking for the final volume, V2. So setup, very simple, just like that. 10 divided by 2, so V2 is equal to 5 liters. The pressure went up, the volume went down, and that's what we would expect. Here's a little bit about the Kelvin temperature scale. It is important that we use the Kelvin scale on these next gas laws. The Kelvin scale is based on absolute zero, so if you're given a Celsius temperature, it is very important that we convert everything to Kelvin before we do the temperature. The next relationship is the temperature-volume relationship. It's called Charles' law. Jacques Charles developed this law in 1787. You'll notice that in his particular law, this chart here, the volume went up. So the volume goes up in those 4 trials. Notice what happens to the temperature. The temperature goes up in a directly proportional relationship. So as volume goes up, temperature goes up, assuming constant pressure. Here's what a direct relationship looks like when you graph volume and temperature. Straight line, positive slope as you graph volume and temperature, which is a direct proportionality. So Charles' law says the volume of a fixed amount of gas maintains at constant pressure is directly proportional to the absolute temperature, which means the Kelvin temperature. Kind of like the derivation with Boyle's law. Volume is proportional to T, but we don't like that proportionality sign. We want an equal sign. So we want to get an equal sign, but you have to introduce a proportionality constant. Again, it doesn't matter what K2 is equal to. It's just a number. K2 is equal to V1 divided by T1. It's also equal to V2 divided by T2. This is what we're accustomed to seeing for Charles' law. V1 divided by T1 equals V2 divided by T2. So let's look at this problem here. Sample of gas at 10 degrees Celsius is heated to 100 degrees Celsius while the pressure is constant. What's the new volume going to be? If pressure is held constant, we don't need it in the equation. My initial volume, we can leave it in centimeters cubed, which is a milliliter. However, the temperature has to be in Kelvin. It cannot be in degrees Celsius. In order to get to Kelvin, we simply take 10 degrees, add 273. So that's 283 Kelvin. Solving for V2, my new temperature is 100 degrees Celsius. 100 degrees Celsius, again, we add 273. It's important that we use the Kelvin scale. So there's our setup, and we can simply solve for V2. Now, if the temperature goes up, we would expect the volume to go up proportionally. So 177 divided by 283, multiply by 373, you will get a new volume of 233 centimeters cubed. Pressure-temperature relationship. The pressure of a sample of gas is directly proportional to the Kelvin temperature if you're at a fixed volume. So the pressure-temperature relationship looks just like Charles's law, except we're substituting pressure for volume. It's a direct proportionality. Okay, so in this problem here, we're looking for the new pressure. We have a constant volume, so we can do the pressure-temperature relationship. My initial pressure, we can leave it in bars. The only thing that matters with these elementary gas laws is the temperature has to be in Kelvin. Pressure and volume units do not matter. So T1 is 25 degrees Celsius. That has to be in Kelvin, so add 273. 273 plus 25 gives you 298. We're looking for the new pressure, P2. T2 is 40 degrees Celsius. When you add 273, you get 313 Kelvin. So again, just make sure your temperature's in Kelvin. The other units for pressure and volume do not matter with these gas laws. But if temperature goes up, we would expect the pressure to go up proportionally. You can solve it and you will get the new pressure, 1.05 bars.